Hi, this is an example problem having to do with energy from chapter 6. Pause for a moment and read the question. So we're given a speed of the roller coaster at the top, and we want to try to figure out what is the speed at the bottom. And we're also given the vertical drop length. To solve this problem, we're going to use energy methods, and we're going to start with the basic equation we can use to solve all energy problems. Here it is. I call this the conservation of energy equation, and it says that the work done by the non-conservative forces plus the initial kinetic plus initial potential energy is going to be equal to the kinetic energy and the potential energy at some final time. Now in this problem, and in any of these type of problems, we want to identify the starting point. So I'm going to pick right here at the top. This is where we start. And again, I'm going to just choose one of the cars, right? And when that car gets down to the bottom here, this is what we're going to call the end point, right? Or the final point, right? And so here's your start, and here's your final. And now in this problem, it says neglect friction and air resistance, which means gravity alone is going to go ahead and govern this motion. So that means that there's no non-conservative forces doing work, right? This is gravity alone. And so we can cross out W and C. And then we see that we've got the total kinetic plus potential in the beginning equals the total kinetic plus potential in the end. The sum of kinetic plus potential at any instant, we call this the mechanical energy. Write it as EMEC. So this tells us that the mechanical energy in the beginning is equal to the mechanical energy at the end. And when something is equal to the beginning and the end, we say that it is conserved. So this is a problem where we have the conservation of mechanical energy. Furthermore, we have formulas for the kinetic energy and for the potential energy. 1/2 mv squared for kinetic potential is mass times gravity times h, the height. And so we want to determine at each of these start and end points what is the value of h and what is the value of v. These are the important things to know. So let's go ahead and see if we can figure it out. I'm going to go ahead and start by doing the h value. So I want to go ahead and draw a coordinate axis here. So h is only straight up and down. I'm going to call this a y-axis. Now I'm free to choose my zero position wherever I want. I'm going to pick it to be at the bottom, the end point. So this is h final equals 0. I chose that. Now up here's where we start. This is h initial, and we know that it's 127 meters above the bottom, so this is 127 meters. I could have put the 0 at the top and put the minus 127 at the bottom. It doesn't matter. Choose your 0, stick with it for the rest of the problem, and you'll be right, whatever you decide to choose. All right, next. We need to write in the speed. So here's the start here. What's the speed here in the beginning? 6 meters per second. So I always draw a picture of this, or the picture was here, and then I go ahead and I label the values at the start and the end. The final speed, we don't know what that is. That's what we're trying to solve for. Now we're going to go ahead and plug in each of these equations into the conservation mechanical energy equation that we have here. And we're going to find out that we end up with this, right? We've got 1/2 m v initial squared, right? I'll go ahead and write the rest, plus mg h initial is equal to 1/2 m v final squared plus mg h final. And we want to solve for v final. And importantly, all we really need to worry about here are the heights and the speeds, which we know everything else because of course we know what g is equal to. And if you look carefully, you can see we can divide both sides of this equation by the mass. The mass doesn't matter in this problem because every term has a mass, which means we can cancel them out. At the end of the day, we're going to end up with some algebra to solve, right? And so I got v initial squared over 2 plus g h initial is equal to v final squared over 2 plus GH final. Let's solve for V final. So I'm going to take the V final over 2, and I'm going to put it on this side. That means that I've got this on the other side, and I had to subtract off the GH final term to move it. Finally, we want to go ahead and multiply both sides by 2 to cancel out the 2. We're going to have V initial squared plus 2GH0. Remember, this is a multiplication by 2. Minus 2GH final. And finally, we can go ahead and square root both sides, and then we'll solve for V final. So the square root of V initial squared plus, let me factor out the 2G because that appears in both terms. And we end up with this equation. Now we just need to go ahead and plug in our values, and we'll solve for V final. So for V initial, we see that that was equal to 6 meters per second, and H initial is 127 meters, and the final height is 0. So we've got 6 meters per second squared plus 2 times 9.8 meters per second squared times a 0 minus a, sorry, I got this backwards. I was going to get a negative number. That would have been wrong. We start up, right, at 127 meters, and then final is 0. And we're going to get a positive number inside the root. And if we solve for this, we'll see that we get an answer that's 50 meters per second. So that's the speed of the roller coaster as it gets down to the very bottom of the track there. So to summarize, if gravity alone governs the motion, as it does in this case, we can cross out the non-conservative work, and then we get an equation for the conservation mechanical energy. Since the kinetic energy depends on the speed and the potential energy depends on the height, we need to look at the initial and final spots, draw a picture of it, and put at the start what is the height there. You get to choose the 0 point of your axis. And so figure out the initial and final heights and the initial and final speeds. Any number that you don't know, there'll be 1. That's the one you're going to solve for in your equation.